good morning, everyone. Welcome to this edition of the NITheCS Colloquium. We are very quantum, always in a superposition of two institutions. Yeah? And thank you very much for joining us at this unusual time. But we have a speaker, Professor Ilya Mandel, who is based in Australia. And the usual time would have been a little bit challenging for him. So Ilya, thank you very much for offering the talk, and thank you very much to the participants for the flexibility in joining us this morning. Yeah? With us this morning is also Jandrew Brink and Marisa Geyer, who know Ilya, and I will ask them just now to introduce him, and they kindly volunteered to moderate the questions during or after the talk. Yeah. So you are all expert Zoomers, so please make use of the Q&A facility or raise your hand. And since we are not hundreds, we can give you the right to pose your question yourself live. Yeah. Okay. Then Jandrew, over to you. If you would kindly like to introduce the speaker.
Okay, thank you very much. So I've known Ilya ever since I met a charming Russian student with a wonderful accent at the California Institute of Technology. He also had the ability to get lost in the mountains on a regular basis and was unfortunately reasonably proud of that. He was supervised by Kip Thorne and worked on the LIGO project. He was initially part of the LIGO collaboration and then left it to be free of all the restrictions there are on publishing there. He's actually made a huge contribution astrophysics-wise, and he's a wizard when it comes to doing order magnitude estimates and population synthesis, and I'm sure he'll tell us a lot about that. After Caltech, Ilya stayed in the US for a bit, when going to Northwestern University and MIT, before settling for quite a long time in the UK. And recently he's moved down south to the Australians to share our summer and to get a very bad time zone. He's currently at the Monash University in Australia in physics and astrophysics. And he does a lot of stellar evolution, gravitational wave modeling, and is a fascinating speaker. So I trust you'll enjoy his accent as well as his intellect in the talk that follows.
Thank you, Jandrew, for the very nice introduction of the speaker. And Ilya, if you would like to start your presentation now, you're welcome to start sharing your screen and show us your slides. Yeah.
Thank you very much for hosting me. Thank you very much for a wonderful introduction, Francesco and Jandrew. I am not sure that my accent is nearly as wonderful as Jandrew claims, nor are my speaking skills, but I will try to do my best. I think I'm very fortunate that I get to speak to you at an unusual time, relatively early in the day. It's before lunch, so hopefully you're not yet in a food coma and won't fall asleep despite the quality of the talk. So that's my best hope. So let me tell you a little bit about this topic that I've been working on for, I guess, close to 20 years now, which is gravitational wave astrophysics. And it's a very exciting topic for me, not just because it's something that I've been working on, but also because really just in the last few years, it's gone from being a theoretical dream to a rapidly growing observational field with a very large number of exciting discoveries and far more on the horizon. And so I'm going to try to tell you a little bit about what we've seen so far and what we hope to see in the near future and what we might be able to learn from that. So we'll return to this title slide or picture, which has to do with how you might form merging compact objects, in particular merging binary black holes that give rise to these gravitational wave signals a little bit later in the talk. For now, let me continue with actually a discussion that Jandrew and I were having just before the start of this talk, which is a conversation about bets. And here on the left is my PhD advisor, Kip Thorne. On the right is his friend, Stephen Hawking. And this is one of the famous bets that Kip and Stephen had made almost 50 years ago now, where they were betting on whether Cygnus X1 is really a black hole or not. And we'll get back to Cygnus X1 in a moment, because there are actually some nice, interesting results on Cygnus X1 that I got to be recently a part of. So it's kind of a thing coming back full circle. But the reason I'm putting this up here is that as recently as 50 years ago, we weren't really sure whether such things as black holes really existed, or whether they were just theoretical predictions coming from Einstein's theory of general relativity. So this field has really been growing and developing quite rapidly. And here's another bet, this one a lot more recent, only about 10 years old. Of course, having seen these bets that my PhD advisor was making on a regular basis, I was always tempted to make one as well. And so in 2011, I had the opportunity of making one. What happened was that these detectors called LIGO and Virgo, which were detectors built to observe gravitational wave signals, and we'll talk a little bit about how you might do that in just a second. But these detectors had been operating since, well, in the case of LIGO, since around 2001. And for the first 10 years, really not observing much of anything. Now, that wasn't entirely unexpected. They weren't yet particularly sensitive. Sensitivity is something that you gain over time with these kinds of instruments as you improve the instrument gradually. But nonetheless, there seemed to be a hint of a very interesting signal that came in on the 16th of September, 2010. And it really looked like a gravitational wave. But one thing we weren't sure about, those of us who were part of the LIGO collaboration and were looking at the data, trying to analyze the data, we weren't sure whether it was a real signal or not. And the reason we weren't sure is that there was a chance that some sneaky people from within the LIGO collaboration might have tried to artificially inject a gravitational wave signal into the data. And you might say, well, why would anybody fake a signal? Well, the reason was pretty simple. Actually, it was twofold. There was two reasons. One reason was to test whether the search pipelines were working properly, whether we would really be able to detect a signal that was injected and analyze it properly. And the second reason was just to keep things a little bit calm, actually, because the hope was that if we could detect this signal, but without being absolutely sure whether it was real or not, people weren't going to immediately start writing messages on Twitter and Facebook saying, yay, LIGO saw something. We would have some time to gradually come to terms with the signal, understand it, and only then maybe once we had tested whether or not there really was an injection, would we be confident enough to announce it, and then the Twitter would open up. Okay, that's sadly not quite what happened a few years later, where there was a lot of premature noise about a possible LIGO detection, in that case a real one. But in this case, it did work. We analyzed the data. We spent half a year very carefully testing it, convinced ourselves that it must have been real in the sense that it wasn't noise. So it was either a real injection or a real astrophysical signal. And then we all got together, the entire collaboration got together. We voted that we're going to open the envelope containing any possible information about a blind injection. If the envelope was empty, meaning there was no injection, then we were going to submit this paper, which we had already written. Of course, if the envelope had something in it, we were going to check whether we detected the thing that was in the envelope. Hopefully the answer would be yes. And then, okay, no paper, but at least some confidence that our data analysis is working correctly. And we had about 10 minutes between the time that we voted to agree to open the envelope and the time that the opening was actually going to happen. And during those 10 minutes, I walked up to Kip and offered him this bet, where I bet that I didn't think it was real because one of my roles was to try to understand how often we ought to be able to see gravitational wave signals, how often do binary black holes merge, and I didn't think they merged nearly often enough. Kip was a bit optimistic. He was really hoping to get the detection, so he agreed to the bet. So this was our bet. Then the envelope was opened. So this was the director of the LIGO lab at the time, J. Marks, who didn't quite know how to spell the word envelope. And sadly, the envelope was full. Fortunately, it was full with exactly the signal we detected, so data analysis was working just fine. Fortunately for me, I won $1. Unfortunately for Kip, he had to concede, as you can see below. Although apparently this broke the record among all of Kip's many bets for the shortest time between bet formulation and bet resolution. And unfortunately for all of us, we then had to wait for quite a while. We had to wait all the way until September of 2015. Because in September of 2015, this happened. Well, not exactly this, but something like this. So this is a soundtrack made by my former student, Jason Tai, of what a gravitational wave might sound like. Now, why am I playing it in the audio band? Why are we listening to it rather than just watching it? Well, because it is in the audio band for the kinds of events that LIGO is observing. So what's a gravitational wave? Well, a gravitational wave, I'm not going to go through and try to solve Einstein's equations on the spot. In any case, there is no analytical solution for the kinds of sources that generate gravitational waves, at least not a complete solution. So it requires numerical relativity, solving these nonlinear differential equations on a supercomputer to really get the full picture, although you can make some approximations for what the signal might be like. But the important point is that a gravitational wave is a ripple propagating through the fabric of space-time. So it's an oscillatory perturbative part to the metric propagating on top of the background metric. It propagates at the speed of light. It stretches and squeezes space perpendicular to the direction of propagation. And for the kinds of sources that LIGO is able to observe, which are sources composed of among other things, merging binaries composed of two compact objects, either neutron stars or black holes, these are sources that LIGO is able to observe in the audible band, meaning between a few tens and a few thousand hertz. So that's why gravitational waves, unlike children, are best heard, not seen. So this was a signal from a 1.4 in a 10 solar mass binary, and the thing to listen to is this chirp-like characteristic. So you ought to be able to hear that as the binary, as the two objects moving around each other are spiraling in because they're losing energy and angular momentum by emitting gravitational waves, the binary gets closer and closer together. As a result, the frequency of the gravitational waves is increasing. Also, the amplitude of the gravitational waves is increasing because there's a stronger interaction as the binary gets closer. And so you hear this characteristic chirp where the frequency and the amplitude are both going up. So let's listen to this again. Let's hear one more of these, but for somewhat different masses. So this was supposedly a neutron star of 1.4 solar masses spiraling into a 10 solar mass black hole. Now let's get two more massive black holes, 14 and 50 solar masses. So the overall general picture was pretty similar. We have this chirping signal, this growing amplitude and growing frequency, but of course the details were different. The rate of change of the frequency over time was different. And that's already telling us something important. It's telling us that not only can we hope to observe a gravitational wave signal, but once we observe it, we might be able to learn something about the properties of the source. Namely, if we're talking about a compact object binary, and jumping ahead, these are the only sources LIGO has seen so far, although there may be some other possible sources in the future. But if it's emerging compact opportunity binary, we ought to be able to learn about things such as the component masses, and maybe even a few other things like the location of the binary in the sky, the spins or the sense of rotation of the black holes and neutron stars. In the case of neutron stars, maybe some tidal deformation, and so on. So here is what has actually been observed so far. This is a plot showing the masses of the objects that have been observed. So on the vertical scale, you have the mass and solar masses. The horizontal distribution here is completely arbitrary. It's just to aid the eye. The yellow objects in the bottom are known neutron star masses. The couple of orange mergers are mergers of two neutron stars that LIGO has seen. The purple objects are black holes that have been seen typically in X-ray binaries. And the blue objects, of which there are now close to 50, actually 100 on here, 50 binaries, each one composed of two black holes, are the mergers of binary black holes that LIGO has observed. There's also one very interesting source, which is a source more or less smack in the middle of the bottom part of the slide, which contains a black hole merging with, well, we don't quite know what, something that has a mass of about 2.6 solar masses. It remains to be seen whether that was actually a particularly massive neutron star or a particularly low mass black hole. By the way, I should say that I am very happy to be interrupted. Sorry, I should have said this earlier. So if anybody has questions, please feel free to ask. And I gather that I won't get to hear your questions directly, but John and Marissa, if you see questions in the chat, then please feel free to interrupt me with the questions anytime. So let's talk about some more bets. My internet connection is unstable. That's not good. Hopefully you can still hear me. Okay, so let's talk about some more bets, because bets are fun. So now that this actually happened before we saw the first gravitational wave signal. I made another bet, this one with a wonderful observer of transients, gamma ray bursts, and their afterglows in particular, Neil Tanver at Leicester University in the UK. And I bet Neil that none of the first 10 LIGO events would have an observed electromagnetic counterpart. Now, here I was sort of playing maybe the same role that I was actually playing in the previous bet, namely I was trying to be pessimistic, but really secretly hoping that I would be wrong. So it was a bit of an insurance bet, right? If I lose the bet, then we get a really cool observation. If I win the bet, well, at least I'm consoled for the fact that we haven't seen any electromagnetic counterparts. Now, to be fair, I did think I was going to win this bet, unfortunately, but, well, maybe not. Turned out I was wrong, because on the 17th of August, 2017, LIGO saw this amazing signal that looked like it might have come from a pair of merging neutron stars. At almost the same time, only 1.3 seconds later, Fermi observed a rather weak gamma ray burst. But the combination of the Fermi observation and the LIGO observation, which seemed to overlap in both time and spatially on the sky, prompted observers to train their telescopes on the source, and it was probably one of the most observed sources ever for that night and the next few days and months and even years. And sure enough, just about 10 hours later, some observers saw, including Neil Tanver and his team, saw that there was an electromagnetic counterpart. This counterpart turned out to be a kilonova explosion associated with the fact that when two neutron stars merge, there is some very rapid nucleosynthesis, so-called R-process nucleosynthesis going on, that produces some very heavy and radioactively unstable elements. And then over time, those elements undergo radioactive decay, and that decay powers a kilonova on a time scale of a couple of days. It takes a couple of days because initially it should be brightest early on, but of course, initially you have this really hot, dense soup of gas. And so you're actually not able to directly observe anything until things become sufficiently optically thin that photons can get out. And that happens after about a day or two. In fact, it actually turns out that basically from seeing just the bolometric luminosity and the decay timescale, you can figure out quite a bit about the source. You can figure out, for example, how much mass there was in the ejecta. And that was one of my contributions to the analysis, because one of the upsides of having lost this bet to Neil Tenver is that I then got to play along as a pet theorist on some of those observing papers, which was a great deal of fun. And then, of course, there were also much longer term observations of radio, X-ray, and optical afterglows from a ultra-relativistic jet smashing into the interstellar medium, initially powering the gamma ray burst, and on longer time scales, powering synchrotron emission. These, by the way, are also fascinating because they are, we're actually learning a lot, and we're continuing to learn a lot, I should say. We're still working on trying to make sense of this event, learning a lot about the interaction of the emission with the interstellar medium, and trying to understand what this is telling us about things like the properties of the interstellar medium, the properties of the kilonova ejecta, the properties of the jet and its lateral structure and its energy structure. So this is really a gift that keeps on giving. Now, let me tell you about another one of my pastimes. And this is trying to understand where these sources, these gravitational wave sources, are coming from. So I think it's actually going to be a pretty easy story to understand where they're coming from. Well, at least maybe at first glance, it's an easy story. So let's suppose we have our two stars. Let's call them Stella and Estelle. And our two stars are a couple. In fact, stars like being together, perhaps a bit like people. And in fact, very few stars, relatively few stars, are singletons. Maybe only a third of the stars are single stars like our sun. The majority of the stars come in pairs. In fact, the more massive the stars are, the more likely they are to have companions. Some of them don't just come in pairs, they come in triples and quadruples. So maybe a bit of polygamy among stars. But let's suppose, for simplicity, these particular two stars are just in a binary. They're orbiting around their common center of mass. And well, one other thing that happens to stars, which may be a little bit similar to what happens to people, is that as they get a bit older, their waistlines tend to bulge a bit. They put on a little bit of weight. Well, they don't really get more massive in the case of stars. They just mostly get bigger. And they get bigger in, sorry, I jumped too fast. So I said, okay, before you tell the story of exactly how those stars merged, let me say that, okay, let's imagine that those two stars each make black holes. I am picking this little image of a black hole from the movie Interstellar in homage to Kip Thorne, who, in addition to being one of the leaders of the in the early days of the LIGO experiment, one of the initial people who proposed it, along with Ray Weiss and Ron Drever. He also, in the last decade, has spent some time being a Hollywood producer, in particular on this movie Interstellar. And this is an actual movie still from Interstellar, showing what a black hole with an accretion disk around it might look like. The accretion disk looks so funny because the black hole is producing extreme lensing, so light from the backside of the black hole, from the accretion disk around the backside of the black hole, can actually get to the observer. But let's suppose these two black holes now happily merge. So as they merge, they're emitting these gravitational waves. Here is a artist's impression of what gravitational waves might look like from a merging pair of compact objects. And then you have on the left Dave Wrightsey, the spokesperson of the LIGO collaboration, announcing the first detection. On the right, there is Kip himself holding his Nobel Prize in Physics, which he shared with Barry Barish and Ray Weiss for this discovery. And life is good. So Now I'm going to try to explain why it's actually not so simple. Sorry, I jumped a little bit ahead of myself from the last time I started doing this. And the reason it's not so simple is shown here. And the reason it's not so simple is that, as I mentioned earlier, when the two stars, as the two stars are aging, they tend to expand a bit. Their waistlines bulge, their radii increase. And that's shown in this plot on the right. So this plot on the right shows that you may start out, let's say if we're talking about a 20 or 30 solar mass star, you might start out with a radius a few times the radius of the sun, but at some point in its evolution, its radius gets to be hundreds, perhaps even thousands of times larger. So hundreds to thousands of times the radius of the sun. Now, just for comparison, 200 solar radii is about the distance from the Earth to the sun, an astronomical unit. So we're talking about stars that get to be much larger in radius than the distance from the Earth to the sun. Conversely, on the left, we show what the separation between two black holes has to be in order for these two black holes to merge within the age of the universe. So just focus on the blue line. The other lines are for more eccentric systems. Ignore them for simplicity. And the blue line is telling you that if, for example, I have two black holes that are 30 solar masses each, they can be at most about 40 or 50 solar radii apart if we want gravitational waves to bring them to merger in the age of the universe. Because gravitational wave emission is a very efficient way of losing energy if the binary is already very close. In fact, during the last fraction of a second preceding the merger, the instantaneous luminosity of a binary black hole in gravitational waves exceeds the luminosity of all of the stars in the entire visible universe combined. So these are incredibly bright sources that, in the sense that they are losing several solar masses worth of energy in a fraction of a second. But that only is efficient when the binary is really close. When the binary is far, gravitational waves are incredibly inefficient. So for example, if you consider the Earth-Sun system, yes, it's emitting gravitational waves, but that process is so pedestrian, so slow that it would take billions of billions of billions of years for the gravitational waves emitted by the Earth-Sun system to in any way perturb the orbit of that system. So we don't have to worry about the sun spiraling or the Earth spiraling into the sun, which I suppose is a good thing. The bad thing is that means that we've got this serious problem. Our serious problem is that we need to somehow bring the two black holes within a few tens of solar radii if we want them to merge by emitting gravitational waves. And yet the stars from which these black holes form at some point are several hundred or even a few thousand solar radii in size. So we've got stars this big, and we need to bring them into a binary this tight. So it's not so much a problem of putting a square peg into a round hole. It's more a problem of putting a peg that's the size of one of those giant sequoia trees into a hole that's the size of a fingernail, right? Try putting two sequoia trees one fingernail width apart, and you'll see why it's so difficult to ever create binary black hole mergers. Okay, so instead of being easy, this is actually very difficult. So we should never see gravitational wave signals, right? Well, that can't be right either, because LIGO has seen them. So the story must be a little bit more complicated than that. So let's just think for a moment about some of the possible ways we might be able to solve this story. And here's a nice artist illustration from, so this was an artist in Nature who kindly made this diagram for a paper that Alison Farmer and I had written a couple of years ago, and it shows some of the possible channels for forming these merging binaries. And the basic ideas are something like the following. Option one, you bring the two stars close together after they've gone through their maximum expansion. So when the stars are start out in a wide binary. Then as the stars grow and interact, something in the process of interaction actually causes the binary to shrink. Option two is the magician's option. The magician takes up his or her magic wand and says, abracadabra, stars, thou shalt not expand. And for whatever reason, the stars listen, don't expand. Now, if that were to happen, then you could start with the two stars very close together, and they would form black holes in place. And they, because they were already so close together, they can merge, no problem. The third option is a kind of matchmaking club for black holes. So now we're going to say, forget about binaries, forget about stars, somehow, okay, somehow make the black holes. Yes, we at some point we had stars that are massive enough, more than about 20 solar masses, will naturally collapse into black holes after only a few million years, because massive stars burn bright and die young. They're kind of like rock stars. So that means after a few million years, they'll make black holes. And then we allow those black holes to interact with each other dynamically, meaning just through Newtonian gravity. And if there is a hot, dense soup of these black holes somewhere, like maybe in a very dense star cluster, such as a globular cluster, then you might organically form black hole binaries, harden them and tighten them, and eventually get two black holes close enough that they're able to merge within the age of the universe. Okay, so let's talk a little bit about these solutions in a bit more detail, and let's maybe start with the first one. So here's the story for the first one. Sorry. And the story here is goes something like this. I'm not going to go through all of the myriad references here. You can see that people have been working on this for quite a long time, just showing you a little schematic. So we have our two stars. One star, the initially more massive one, evolves a little bit faster, starts to expand, as we said, expands until the tidal gravity from its companion starts ripping off some mass from that initial star. That star loses its hydrogen-rich envelope, leaving behind a helium core, what's called a Wolf-Rayet star. Meanwhile, and eventually that core continues to evolve. That's an even faster process, because most stars spend 90% of their life on the main sequence, where they're burning hydrogen in the core, and then all of the other steps in their evolution, burning helium, burning carbon and oxygen, through to neon, magnesium, silicon, and eventually all the way until you form an iron core. That whole process takes less than 10% of the life of the star. So eventually the star creates an iron core. At that point, there is no more exothermic reaction to provide the pressure to prevent the star from gravitational collapse. So the star begins to contract, and if it's massive enough, it will make a black hole. If it's a bit less massive, maybe initially between 8 and 20 solar masses, it will make a neutron star. If it's not even 8 solar masses, it will make a puny white dwarf. And white dwarfs are wonderful, but we won't talk about them here because LIGO can't detect them. They break apart at orbital frequencies of less than a hertz, and LIGO is not sensitive at frequencies that low, so they're not interesting for us for the purposes of this talk. So, but let's suppose that the initial primary star makes a black hole. Now the secondary's evolution kicks in. The secondary runs out of hydrogen in its core. The core contracts, the envelope expands. There is mass transfer onto the primary. At this point, the binary is still very wide, but this mass transfer onto the primary becomes dynamically unstable. I won't go through the details of why that's happening, but essentially the star is trying to give mass to the black hole, and the more mass it gives, the more the stronger the tidal pull in the star becomes, and so it wants to give more and more and more mass to the black hole in a runaway process. The black hole can't eat all of that mass quickly enough. It's like being fed through a fire hydrant, and so instead all of this mass from the star ends up becoming a joint common envelope around the entire binary. And in fact, this is called a common envelope phase. So now you have the core of the secondary star and the primary, which is now a compact object, spiraling around each other inside this envelope of gas. Of course, as they do that, they experience drag. It's like trying to swim through molasses. So that means that they are losing their kinetic energy ultimately their orbital energy, and that energy is instead going to heating up the envelope. At some point, what might happen is that the envelope has enough energy dumped into it that the envelope is ejected altogether from the binary, and instead the remnant, what you're left behind with, is a much more compact binary because it has lost a lot of its orbital energy. So you were left behind with a far more compact system. And now this system might become two compact objects, two black holes, and it might in fact merge within the age of the universe, because now you have, in the process of taking all of this orbital energy out of the binary and dumping it into the common envelope, you may have tightened the binary by a factor of several hundred, allowing you to now merge within the age of the universe. So that's the so-called channel for isolated binary evolution through a common envelope phase. There are a couple of other channels. I'll just very briefly mention them. So one, chemically homogeneous evolution, is one that Selma Dominck and I have been sort of among the lead developers for. And it's this idea of the magic wand, stars thou shalt not expand. Now, the way you can prevent a star from expanding, it turns out, is by never letting it reach a point where you have a helium-rich core and a hydrogen-rich envelope. Because once you get there, the helium core will contract, and through a mirror principle, the hydrogen envelope will expand, and the stars get radially big. But what if you could manage to very efficiently mix the star? You had a little mixer, and you were constantly taking helium, which is a hydrogen fusion product, out of the core, putting it into the outer layers of the envelope, and bringing in fresh hydrogen from the envelope into the core. Well, in that case, you could continue this process all the way through until the entire star was made up of helium, there was no hydrogen envelope, and then there is no need for an envelope expansion. So the star actually shrinks in radius as it gets older rather than expands. That means you put the two stars very close together, they remain very close together, and eventually they merge by emitting gravitational waves. Wonderful, after they've made black holes. So how do you operate this mixer? Well, it actually turns out that putting the stars very close together is exactly what allows you to mix them. Because if you put the stars very close together, they become tidally locked. They become tidally locked, meaning that the tides are strong enough that if the stars were rotating at a frequency different from the orbital frequency, then they would experience a lot of sloshing around. And that sloshing around is dissipating energy, so it's not the most energy efficient configuration. Of course, physics prefers an equilibrium configuration, which is minimizing the energy. And so the most energy efficient configuration is to ensure that the rotational period of the stars is the same as the rotational period of the binary. Now, this only happens if the binary is compact enough, if it's tight enough, because tides aren't very efficient in wide binaries, but they become very efficient if the binary is closed because the perturbations are much stronger. So this energy dissipation, if the stars are not tidally synchronized, is greatest in closed binaries. So then if the stars are forced to, by the fact that the binary is closed, are forced to very rapidly rotate, it turns out that it's that very rotation that's acting like a mixer and causing the stars to efficiently mix. And so this is called chemically homogeneous evolution, which is just a fancy way of saying that there is no gradient across the star in terms of the species. So there is the same concentration of helium and hydrogen everywhere throughout the star. The third object is this dynamic, or the third scenario is the dynamical formation scenario, where, as we've said before, it's all about Newtonian interactions. Turns out that you pretty quickly form binaries because massive stars mass segregate towards the center of a dense stellar environment, like a globular cluster. Then once you have those stars mass segregating, and you form binaries naturally, when binaries experience interactions where an interloper flies by the binary, that interloper in the process of an interaction typically ends up sharing energy with the binary. If the binary is tight enough, meaning the binary's orbital velocity is much higher than the typical velocity dispersion in the cluster, that means the interloper will gain energy through this interaction. And of course, if it gains energy, conservation of energy tells you the energy must come from the binary. So the binary must shrink. So the binary is actually acting as a heat source for the cluster. And after several interactions, the binary can shrink enough to the point where, again, gravitational wave radiation can take over and the binary might merge. So this is the so-called dynamical formation scenario. Now, okay, I've spent quite a bit of time telling you about these scenarios. Now, where do we go from here? Well, the job of a gravitational wave astronomer is a little bit akin to the job of a paleontologist. So, of course, the paleontologist has never actually seen a living, breathing, walking dinosaur. All she ever gets to see are the bones, the fossils of the dinosaur. But if the paleontologist understands the process by which those fossils form, then perhaps the fossils can be used to go back and to figure out from the appearance of the fossils, what do the teeth look like, what's the shape of the jaw and so on, what kind of dinosaur this was. So without ever having seen the dinosaur, the paleontologist can study the fossils and say, oh, it was a herbivore, or it was a carnivore, or if it was a carnivore, did it hunt alone, did it hunt in groups, and all of these other fascinating facts about the dinosaur. So we're trying to do something similar, because for us, these black holes and neutron stars, you can think of them as remnants as fossils of stars. They are what stars leave behind at the end of their evolution. And so even though gravitational wave observatories only get to observe the last few seconds or fractions of a second in the lifetimes of these stellar binaries, they are fascinating observations because they allow us to jump back and ask the question, how did the stars get there? How did these black holes get there? What is this telling us about stellar evolution, about binary evolution, about the dynamics of dense stellar environments, and so on? So this is essentially what my research group is doing. So we call ourselves COMPASS, Compact Object Mergers, Population, Astrophysics, and Statistics. It's mostly a backronym. But we're really trying to understand the inverse problem of gravitational wave astrophysics. We're trying to figure out how to go from a population of observed sources to understand the key uncertainties about stellar and binary evolution and binary dynamics. And one of the ways in which we do that is that we create forward models of how stars and binaries evolve. So we sometimes call this population synthesis. So we start out, because actually it turns out that only a very small fraction of stars go on to make merging binary black holes and merging binary neutron stars. Most stars do something else. Maybe they aren't massive enough to make neutron stars or black holes. Maybe they are massive enough, but at some point they they just merge in the binary long before they make compact objects, and so LIGO never sees this as a source. Maybe the binary is too wide and you make two black holes, but they take longer than the age of the universe to merge. No chance of seeing that. Maybe the binary is disrupted by a supernova kick, because when supernova go off, when a star collapses into a neutron star, it gets some natal kick because there's some asymmetric ejection of material during the supernova, and that's enough to kick the remnant. And if the remnant gets kicked hard enough, the entire binary is disrupted. So of course, great, now you have a neutron star, but it's not going to merge with anything. So only a very small fraction of possible binaries lead to neutron star mergers of binary black hole mergers. Maybe for every million solar masses of star formation, only a few compact object binaries are ever formed. But that means that we really need to simulate a very large set of binary stars in order to understand which of them and under what circumstances are going to create merging compact object binaries. And then we go about trying to compare our predictions against observations. And we try to say, what have we learned? Because there are lots of uncertainties about binary evolution. And so we might not actually create one mock population, we might create several mock populations, and then ask the question, which of those mock populations is a best match for the observations? Now, I'm going to run out of time, so I'm not going to show you all of the slides. I will save you some time here. But let me actually come back to something that we touched on early on. I hope I have the right slide. And that's some discussions about the future. So what's the goal of this? Well, the goal of this is to bring together observations. And by the way, I don't just mean observations of gravitational wave sources, but also other kinds of observations. We care about observations of gamma ray bursts, of X-ray binaries, kilonova, supernova, and so on. Figure out the kinds of questions we can answer, combine those observations and those observational constraints together. So this picture I've taken is actually taken from a talk by a cosmologist, but the point is that if you have different kinds of constraints, they might have different degeneracies, but together they might overlap only in some small portion of the parameter space, and that tells you what the true answer is. So can we do a similar thing and find, among all of these uncertainties about stellar and binary evolution, one set of solutions that is going to match all of the existing observations? And it's very much something that we're in the process of doing. But since I started my talk with the discussion of bets, I figure I should return there. So here is another bet. This bet was, I actually was not a participant in this bet. I was an adjudicator for this bet. So here are my friends and colleagues, Shurab Chatterjee, Carl Rodriguez, going from left to right, myself, Daniel Holtz, and Chris Belczynski. And this was at a meeting in Aspen a few years ago. And we signed this bet asking whether or not there would ever be black holes in merging compact object binaries in the range between 55 and 130 solar masses. And the reason we picked this funny range is that it is thought that through normal stellar evolution, there should never really be black holes formed in this mass range, because stars that would have made black holes in this mass range will in fact explode in pair instability supernova, not leaving any remnant behind. So what happens is these stars are so hot towards the end of their lives, the temperatures reach about 10 to the 9 degrees Kelvin, and that means that some of the radiation in the stars, which is actually providing most of the pressure support, so the stars are largely being supported by radiation pressure at this point for these very massive and very bright stars. The photons spontaneously pair produce positrons and electrons. And as they do this, the radiation pressure support drops, the star begins to contract. As it does so, it gets even hotter. Because it gets even hotter, even more of the photons spontaneously pair produce. Therefore, the pressure support drops even more. The star contracts even further. It turns out it's a runaway process. It leads to explosive oxygen burning and eventually a very bright explosion in a pair instability supernova, or at least so the stellar theorists tell us. There haven't actually been convincing observations of pair instability supernova, but assuming that this is true, then we shouldn't be expecting to see these kinds of signals. And so we made a bet whether or not this would be seen. This bet was made in February of 2017. A couple more people, Stan Woosley and Fred Razio, joined this bet on different sides. And lo and behold, in May of 2019, there was another event observed by LIGO. Here are the signals. So in blue is the actual data from the LIGO instruments, the function of time. You see that it's fairly noisy, but there's a clear signal standing up above the noise. You can even see it better on the spectrogram. And if you figure out what the masses were from these signals, here the masses aren't very well measured because you only get to see a few cycles for these very massive signals. But it's pretty clear that the more massive object is somewhere around between 70 and 90 solar masses. And if that's true, that means that we did see an object in emerging binary, a black hole in the mass gap. So that resolves this particular bet. And I had a funny dual role here because it turned out that I was actually the referee of this discovery paper. By this time I had left the LIGO collaboration, so I got to referee this paper. And then after accepting this paper publication, I also got to adjudicate the bet. So that bet was finished. So far, so good. Exciting discovery. There are more bets, of course, that are still to be resolved. Like, for example, are we ever going to see eccentric sources? We still don't know whether that's true. Eccentric sources would very confidently point to dynamical formation, because, of course, you can make an eccentric binary black hole through isolated binary evolution, but it takes such a long time before that source moves into the LIGO band that by the time it's in the LIGO band, it will have circularized. Gravitational waves tend to circularize binaries, but that's not necessarily the case for at least a small subset of dynamically formed sources. So that's an open bet. We have a bet still outstanding that was just signed recently with Thor Brokharten about exactly where the boundary lies between neutron stars and black holes. And in particular, this 2.6 solar mass companion I mentioned earlier is maybe going to help us figure out where this gap really lies. Sadly, I had missed my, I have missed a slide. I might find it later. Must have accidentally taken out of this talk, the slide on Cygnus X1, because I was going to return to where we started. Remember, we started this bet with whether Cygnus X1 was actually a black hole or not. Now we know for sure it is a black hole. In fact, we've known for sure it's a black hole for more than 30 years. Stephen Hawking conceded this bet to Kip more than 30 years ago. But it actually turns out that in some very recent observations made with a team of observers led by James Miller Jones, and I had, again, the joy of being the pet theorist on that project. So these guys managed to remeasure the masses and figured out that Cygnus X1 was actually a whole lot more massive than previously thought. It's a whopping 21 solar masses. Now, you might not think that it's very much, given that some of the LIGO signals we were talking about have been clocked in at 30, 40, 50 solar masses, but Cygnus X1 is actually nearby in our own galaxy. And it's very interesting because that means that even in the environment of our own galaxy, where for various reasons people previously thought that we couldn't make very massive black holes, the answer is we actually can make black holes of this mass, and that's already telling us quite a bit about stellar evolution. So that means that really there's and by the way, that observation was not a gravitational wave observation. That's an observation of an X-ray binary. So these Cygnus X1 is still an ongoing binary. It's far away from merging. One companion is a 21 solar mass black hole. The other one is a 40 solar mass main sequence star in an orbit with an orbital period of just under 6 days. In any case, this is really a wonderful time to be playing around with black hole astrophysics and neutron star astrophysics. There's a lot to learn, lots of bets to resolve, and I'm really enjoying it. And I hope you enjoyed hearing about it. Thank you.
Thank you very much, Ilya, for a very interesting talk. I think this was the first bet-driven colloquium that we ever had. So let's see if there will be a new bet in the question and answer session. Can I ask Jandrew to start guiding us through the Q&A question, and Marisa as well, please. Sorry, Marisa, I forgot about you.
That's true.
Okay, so currently there aren't any questions that I can see, but I have.
Yeah, sorry? There are two participants that raise their hand, and I will, while you ask your question, I will give them the rights to talk.
Okay, yeah, so please do that. So I have actually several questions. My first question, Ilya, has actually to do with what has been learned about the spins. Now, I know LIGO can't really localize the spins that well, but what were the latest data that you've had with the latest 50 events? Could you summarize about the lessons learned since I saw you last?
Absolutely. So Jandrew, you're absolutely right that spins are difficult to measure. Individual spins are particularly difficult to measure. There's one combination of spins called the effective spin, which is a kind of mass average spin along the direction of the orbital angular momentum that is relatively easier to measure. And that's the spin parameter that's best measured. If you've read LIGO papers, this is called chi-effective, the effective spin. Now, there's actually some debate about exactly what these measurements are telling us, because so far, on an individual event by event basis, the statement is that there are plenty of events where the effective spins are consistent with zero, meaning that the error bar on the measurement overlaps zero effective spin. Now, of course, I should say zero effective spin does not mean the black holes are not spinning at all. It could be that both black holes are not spinning. It could be that one is spinning up and one is spinning down. It could be that both are spinning in the orbital plane. But in any case, at least some of them, the majority of them, are consistent with there being no spin. And a small subset shows clear evidence for positive effective spins. In some cases by many sigma, inconsistent with zero. Now, the tricky part comes, so that might tell you, at least it tells me, that there is some set of binaries where we see clear evidence of positive spins, and some set of binaries where perhaps the black holes aren't spinning very rapidly at all. And I actually think that's very consistent with the picture I might expect from isolated binary evolution, because most of the time, I expect the black holes to be non-spinning because the bulk of the angular momentum lives in the envelope, just because the moment of inertia is so much larger there. And when the envelope is stripped off, and as you saw in our story, the envelope usually is stripped off, it leaves behind a very slowly spinning black hole. Except that in some cases, tides can spin up the remnant before the black hole is formed. And in that case, you might get some positive effective spin. Now, the LIGO collaboration has analyzed the data using a overall model for what the population of spins might look like. And they actually concluded that the most likely explanation is that there has to be a broad distribution of spins, some spins being positive and some spins being negative. And the fact that they argue that the population supports there being some negative spins, even though no individual events favor negative spins, in their view, that argues that at least some of the binary black holes are coming from the dynamical formation scenario, because that's the one scenario where you expect isotropic spin-orbit misalignment angles. So that's still a topic of debate. And I would say several people, and there's continuing work on this. There's some nice work, for example, from Javier Roulette from the IAS group, arguing that, essentially along the lines of what my gut is telling me, that there is really no evidence for negative effective spins, and therefore the population is very consistent with isolated binary evolution. But the LIGO collaboration is for now taking a different view. So let's see what happens there.
Okay, so I have another question, a follow-up on that, but I rather have one question that I'm going to ask you first, actually quite a good one. It's from Anna, and I can't pronounce your surname.
And Jandru, Anna has the right to speak. So if she would like to ask her question directly, she's most than welcome to do it now.
Okay, I think so. That's a good plan.
Hi, can you hear me? My settings are
I can.
Yes.
Great, thank you. Firstly, thank you for the lovely talk. I had a blast. It was incredible. So I have a barrage of questions for you. The first sort of being about the EM counterpart to a gravitational wave signal. So is it possible that in the case of previous events, there was electromagnetic radiation that just happened to be missed? And going forward, is it kind of conventional nowadays to target EM detectors towards a gravitational wave event before really identifying the source?
And that's a great question. So the challenge with LIGO is that LIGO is really not very good at localizing events on the sky. It's basically, it kind of does a little bit like what your GPS does. It does timing triangulation. So there are 3 different observatories in the network, 2 in the US, part of LIGO proper, and one called Virgo in Europe, in Italy. And essentially you can tell where the signal is coming from by asking for the times of arrival of the gravitational wave signals in 3 detectors, right? So for example, if the signal arrives sooner in Virgo than in the LIGO detectors in the US, that means that the direction is, kind of on the side of the sky, above Europe rather than above the US. That's the kind of localization you're getting. Now, it's a little bit better than that, but it's still pretty lousy in the sense that we're typically talking about localizations of tens, sometimes hundreds of square degrees. That means that you cannot go and point a telescope like Hubble, for example, directly at a source because it has a very small field of view. So what you have to do is point some wide field of view telescopes first. But of course, wide field of view telescopes generally are a whole lot less sensitive. And indeed, there are campaigns that try to follow up all events. They typically have the least sensitive telescopes. There are some campaigns that try to follow up only the promising events. So initial LIGO analysis will often tell us roughly how large the air box is in the sky and roughly how distant the source is. And if it looks like the source is relatively nearby, perhaps only a couple hundred megaparsecs away, and if the air box is small enough that there's a good probability of tiling it with observatories, then you follow it up. Otherwise, you say, okay, their telescope time is expensive, we'd rather follow up something else. And so that absolutely means that it's quite likely that some of the other events had some kind of electromagnetic counterparts, at least other sources involving neutron stars. Whether you believe that there could be a counterpart to a binary black hole merger is a separate story. I personally think it's rather unlikely because you really need matter to power an electromagnetic counterpart. But if you have binary neutron star mergers, it's very likely there were electromagnetic counterparts, and they just haven't been detected, for example, for the one other confidently detected binary neutron star merger so far. And there have also been a few other candidates. So this, unfortunately, so far, only one gravitational wave event had a convincing electromagnetic counterpart, but it was very convincing, and that was really, that was worth the wait.
Right. Okay, that's fantastic, and it makes a lot of sense. And I guess that's why something like Kagra is so important. And then sort of a kind of follow-up question to your answer to Jandra's question. You mentioned that you expect non-spinning binary black holes. Does that mean that a sort of Schwarzschild analysis would work quite well instead of going into a kind of chaometric approach?
That's right. So indeed, so that means that if the black holes are really, both black holes are slowly spinning, it makes for a simpler solution, a smaller parameter space. Both black holes are going to be Schwarzschild black holes, the reduced parameter space in this case means that, in fact, other parameters could perhaps be more accurately determined in that case. Absolutely.
Right. Okay, cool. Thank you. And then just one last question that's a little bit off topic, but how much faith do you put in gravitational waves telling us about the early universe, like in terms of things like electroweak symmetry breaking and phase transitions in sort of like the inflationary epoch?
So I should say that I am in no ways an expert on this. So you probably shouldn't trust my opinion too much. I think there are some very exciting prospects there, and one of the main reasons for why they're exciting prospects is that gravitational waves interact so weakly with matter. The coupling is extremely weak, which means that gravitational waves, at least in principle, you can observe from very early in the universe, whereas for example, you can't really see any photons from beyond the surface of last scattering, which is where you see the cosmic microwave background from, but that's still a time when the universe is about 300,000 years old. So no photons from the first 300,000 years of the universe, ever. No chance. But with gravitational waves, you might be able to see, in principle at least, the first few seconds of the life of the universe. So that makes it very exciting. The question, of course, is how realistic is it that there is a strong signal there, and in what frequency band that signal would appear? Is it actually feasible given the extreme redshifting that we would be able to detect it, even if there was such a signal? But people are looking, and not necessarily even directly with gravitational wave detectors, but for example, people are looking for signatures of gravitational waves in the polarization of the cosmic microwave background itself. So there can be some indirect observations of early universe gravitational waves through impact on electromagnetic observations.
Wow, okay. Okay, great. Thank you so much. And thank you for the wonderful talk. I'll leave the floor to other people now. But thanks again. Lovely talk.
Thank you.
Are there any other questions? Or can I ask?
I think
So
Yinze
there was
had a
also,
question.
yeah, Yinze Ma also now has the right to speak. I think maybe we could give him a go.
Okay, thank you, the chair. Am I audible? Just to check. Am I audible?
You are?
Am I audible? Can you hear
Yes,
me?
yes, we can hear
Yes.
you. Yinze. We can hear you clearly.
Oh, okay, great. Yeah. Thank you, Ilya, for the wonderful talk. And I think I just have two brief questions. One is that you have mentioned a physical reason that why you and others have this bet of not seeing 50 to 100 solar masses black hole. And I think I understand your physical is a wonderful explanation, but eventually you guys see it. and I didn't hear the explanation why the previous physical explanation was wrong. I mean, why you could see it, and that's one question. The other thing is that I see there's a joint constraint on the mass M1 and M2, which showing in a triangle plot, and in the contour there is like a gray triangle region seem to hash out some of the unprobed parameter space for mass. But then later, when you but on the upper and right part of the marginalized mass, then it seemed to be fine to obtain the full likelihood and what's going on there. Yeah, that are my two questions. Thank you. Hello.
Great, yeah, hello, great questions. Okay, so
Yeah,
your
thank
first question was why, what are the possible reasons why we might see, after all, a merger of two binary black holes where at least one companion is in this pair instability supernova mass gap. So yeah. We don't know exactly why this happened, but at least one likely culprit is dynamical formation. If you get to reuse the merger product. So you might imagine that if you're forming things dynamically, then unlike an isolated binary evolution, right, where, okay, you have a binary, the two black holes merge, you have now one black hole, and this black hole just sits there forever, and you never get to use that black hole again for anything else. If you really have this soup of black holes, you merge a binary, you create a new black hole. Now that black hole, if it's still sitting in the same cluster, might now interact with another black hole or another binary, might substitute in through a dynamical interaction, and might go on and have another merger, a second generation merger. And maybe the product of that goes on and has a third generation merger. So you can build up increasingly massive black holes that way. And at some point, you might end up with a black hole that was built up all the way until its mass is in the mass gap. That's why the people who were betting in favor of there being black holes in the mass gap were all proponents of the dynamical formation scenario, Fred Razio, Shurab Chatterjee, and Carl Rodriguez. Now, there are some problems with that picture, though. And one of the problems is that when two black holes merge, unless the merger is perfectly symmetric, meaning that the two black holes have the same mass and they're non-spinning, there is an asymmetry in the way that gravitational waves are emitted. Because black holes just before merger are moving very quickly. They are moving at a significant fraction of the speed of light. That means that any radiation, you can think of gravitational wave radiation as a kind of Bremsstrahlung radiation, right? Radiation from an accelerating electron. And if you imagine that the source of your radiation is moving very quickly, the radiation is very strongly beamed. That means that the gravitational radiation ends up being increasingly strongly beamed late in the merger process. And that means that there is an asymmetry that develops. And of course, because gravitational radiation is carrying away momentum, that means that if there's a net asymmetry, the merger product ends up with what's called the gravitational wave recoil kick. It goes in the opposite direction from the bulk of the momentum carried away by gravitational waves. And that kick can actually be quite large. Even in the absence of spins, it can go up to about 180 kilometers per second if you have a mass ratio of about 3:1. And when there are spins present, if they're in an unfavorable configuration, the kicks can go up to about 5,000 kilometers per second. Now, for comparison, the escape velocity from a globular cluster is only about 50 kilometers per second. Globular clusters they don't have a potential that's all that deep. And that means that you might actually imagine that it's very difficult to form second and third generation mergers because you're so likely to eject the merger product through gravitational wave recoil kicks. And so that's one of the ongoing, again, areas of study. Obviously, there's some disagreement on this. So I'm trying to sit on the fence a little bit right now and present both views on this, but let's say there is still ongoing debate about how often can you actually have these successful second and third generation mergers that would populate the mass gap. Now, your other question, I'm going to let me see if I can share my screen for a moment, just to make sure that we are hold on 1 second, looking at the same plot. Hold on. I think this was the plot that you were talking about, and you were asking why there is a great triangle here.
Yes.
Yeah. Okay. So this great triangle is purely artificial. It just is saying that the way that the LIGO data analysts are defining what is M1 and what is M2 is that M1 is the bigger mass and M2 is a lower mass. So anything that's on this side of the inside the great triangle would have a M2 larger than M1, and that's just not how they're defining things. So basically, this parameter space is just ruled out by their choice of definitions. I should say here that this is not a typical posterior plot because here the masses are very high and you only get a few cycles. The more typical posterior, I don't actually have a posterior plot that's particularly useful here, but maybe I can find one. Okay, that's, let's trust this one a little bit. So here, look at the orange one. That's actually a more typical posterior plot. So this is a posterior for a different event, GW 15, 12, 26. And you can see it looks like a banana here in the M1, M2 plane. So that's actually more standard because it turns out there's one combination of masses called the chirp mass, which primarily at lowest order drives the frequency evolution of gravitational waves and is therefore well measured. There's a combination that's effectively perpendicular to this banana. So, the banana is thin this way because that particular mass combination is well measured. And there's a different combination, which is more or less the mass ratio that goes along the length of the banana, and that's relatively poorly measured.
Okay, thank you for the explanation.
Sorry, I'm trying to stop sharing my screen, but I now cannot find the, stop share. There it is. Okay, sorry.
I don't know, Marisa and Jendru, are there more questions that the two of you would like to ask? And as a final
I'm just double checking if there's nobody else. I've got a final question, but it's as Ilya, as you spoke, I realize I'm asking this on behalf of someone because I'm supervising a student, I'm mentoring a student, so I don't know the field that well, who's very keen on this last event that you were showing. We just had the plot up, so you might have to bring it up again. But maybe you'll recall that after it came out, because you just said the merger is so short, that there's some theorist wondering whether in fact these weren't black holes, but rather something like a head-on collision of boson stars. So this is a weird realm of theory maybe, but I would very much like to tell her what your opinion is on where you would lie with this bet. Do you think those are black holes, or could they be like Broca stars? Or
so here's a challenge. We unfortunately, it's very hard to because there were only a few cycles present, and the reason there are only a few cycles is because the masses are so high that the masses basically set the frequency. So the frequency goes as the inverse of the mass, that means that the higher the masses, the lower the frequency. But detectors on the ground are only sensitive starting with about 20 or 30 hertz because there's just too much microseismic noise below that. The Earth is shaking, and it's very hard to decouple that from the detectors. I didn't talk about the detectors at all, but these are because that's not my area of expertise, and probably you've heard other talks by people who have spent their time actually building these amazing detectors. But there's a lot of seismic isolation that goes on to make sure that you're really seeing gravitational waves rather than the shaking of the ground, but it's still not perfect, and therefore it's really hard to look for low frequency signals. If you want to do low frequency, you really have to go in space. So LISA is a planned spaceborne detector, and that's going to be sensitive at typical frequencies of a millihertz. If you want to go for low frequency events, that's the way to do it. But on the ground, it's very hard to go to frequencies that low, which means that we only get those last few cycles just before merger or during merger. And that makes it very challenging to figure out exactly what's going on. So I think it's true to say that the observed signal doesn't seem to be very compatible with a merger of two black holes that were that had no precession, were in a circular orbit, and otherwise, looked like nice, simple black holes. Yeah. So that means that there was something that was slightly weird going on. But the problem is that, saying that our very simplest model doesn't quite fit and saying which of the more complex models fits is a very different story. So we know the simplest model doesn't quite fit, but actually, because all you need is to tweak one parameter away from the simplest model, and because there's so little data, that's enough to make things fit. So there have been papers saying, well, all you need to do is allow for precession. Precession meaning that you have two spins and they are not perfectly aligned with the orbital angular momentum, they're a bit misaligned. And if they're misaligned, that means that the orbital plane is actually wobbling around as the black hole precesses. It creates a much richer signal morphology, and that's enough to explain the weirdness. Other people said, oh, forget about precession. We don't need precession. We can make them be, non-spinning or spin aligned, but we'll allow for eccentricity. So the binary is not perfectly circular. The binary is eccentric. Well, if it's eccentric, that's possibly enough to explain the weirdness in the signal. Other people, as you say, have said, well, maybe they aren't quite black holes. Maybe there's something more weird going on about them. So we shouldn't be modeling them as just perfect simple black holes. And again, you can explain the signal that way. So I think, unfortunately, we don't know which of those explanations is the right one, but the Occam's razor is
not constraining.
Right, it's just not constrained. The Occam's razor in me says, look, we know it's not the circular non-spinning binary, fine, but I would say probably, if I had to guess, I'd say, okay, precession is the simplest variation because, okay, all it takes is a little bit of a kick at some point, and you misalign the spins. That's reasonable, especially if it's dynamically formed. You don't expect them to be perfectly aligned. The next more complicated explanation is it's an eccentric source, probably not an eccentricity of 1, but an eccentricity of point few, which seems to be enough. And okay, and even if at some point we have better data and we see more signals like this, and both of those are ruled out, only then would I say, okay, now let's look for even more strange explanations that say these are not black holes. But that's just an Occam's razor argument. There's no data to support this particular view.
Cool, thanks. I'll convey that message. Thanks so much for explaining it in so much detail.
Okay, thank you very much. If it seems that there are no more urgent questions, and should questions pop up, we'll be happy to forward them to Ilya later. So Ilya, thank you very much for a really exciting talk. It was really very interesting. And I would like to thank also Marisa and Jandrew for being with us this morning, introducing you and coordinating the question session. And I also need to thank the other Ilya, who is always kind enough to act as co-host of this event. Yeah. So Ilya, thank you very much.
May I also add one more thing? So I wanted to thank, I want to thank all of you, of course, and you as well, Francesco, but I also wanted to add thanks to Renee, who was instrumental in getting this organized. So thanks very much to all of you for inviting me and for hosting me virtually.
Thank you very much, Ilya. And Renee is, I think, is still in the audience, so she heard it firsthand. Yeah, but I'm sure we will communicate via email in the coming days. Yeah. So thank you very much again. Then to you, Ilya, probably a good evening, and to the rest of us in this part of the world, a good day. And please stay all safe, because until we are all vaccinated, it's better to be careful. Yeah. So thank you very much. And Ilya, hopefully one day very soon you will be able to come and visit us again here. Yeah.
I would love to. Thank you.
Because usually we invite our speakers for dinner, but it's a little bit challenging at the moment. But don't forget, you have an open dinner invitation back in South Africa one day. Yeah.
I would love to take advantage of it. Thank you.
Thank you. Thank you very much. Have a good day, everyone.
Bye.
Bye. Bye. All the best. Thank you.
Cheers.
Bye.
Cheers. Thank you very much.
Bye-bye.